There is this deeply ingrained, really comforting expectation we have about motion.
Oh, absolutely.
It's an expectation of linearity, like drawing a perfectly straight line on a map with a ruler.
Right.
You get in your car, you press the gas pedal, and you go forward. Your brain just, understands it. The physics feels completely intuitive.
It does. I mean, it's straightforward, both literally and conceptually.
Yeah.
What you're describing is essentially Newton's first law, but dressed up in its most cozy, everyday disguise.
Right. The idea that
an object in motion will simply stay in that uniform straight line motion indefinitely.
Yeah.
Unless, something messes with it.
Exactly. It's clean, it's comforting. As humans, we fundamentally like things to be headed in a clear, predictable direction.
We do.
But then you turn the steering wheel, you step out of that straight line and into the world of curves, of rotations, of planetary orbits.
And everything changes.
And suddenly that comforting linear reality is entirely shattered. We find ourselves looking at a kinematic landscape that is honestly completely counterintuitive the deeper you look into the math.
Oh, it is the absolute definition of a mathematical rabbit hole.
Yeah.
Because the moment you introduce a curve, like literally any curve at all, you introduce a constant state of acceleration.
Even if your speedometer doesn't move.
Right. Even if your speedometer never twitches.
And that bizarre reality is exactly what we are going to explore today. So welcome to the deep dive.
Glad to be here.
We are pulling from an absolutely massive stack of research today to answer one fundamental question, which is, what actually happens to the physics of the universe when things start to spin?
It's a big question.
It's huge. We've got a mountain of material in front of us. I'm looking at, 17th century mathematical proofs from Isaac Newton,
Classic.
alongside highly technical debates from modern physics forums like Physics Stack Exchange. We've got foundational textbooks, deep astrophysical papers on planetary orbits.
And some surprisingly grounded real-world manuals, too.
Oh, right. Yeah. We are even looking at the literal engineering manuals for modern biomedical centrifuges and industrial dairy equipment.
It is a staggering range of material.
It really is.
But, it is completely necessary. Because to truly understand the mechanics of circular motion, you have to look at it from every conceivable angle.
Right.
We're going to unpack the strict definitions of centripetal and centrifugal forces, and we're going to do it without shying away from the heavy geometry.
Exactly. Because we know you, the listener, you don't just want the surface level summary here. You want the actual mechanics.
You want the real math.
Yeah, you want to know why the universe behaves this way. So we have gathered all of this dense material to make you the absolute center of attention today.
Wow. Very subtle. I see what you did there.
Hey, I couldn't resist. I had to. But honestly, to truly understand this concept of the center, we have to take a massive step back.
We really do.
We can't start with modern centrifuges. We need to go back to, the 17th century?
That is definitely the right place to start. The mathematical description of uniform circular motion, which is really the bedrock of what we're talking about, was originally derived in 1659 by the brilliant Dutch physicist Christian Huygens.
Right, Huygens.
But it was Isaac Newton, a few decades later, who really gave us the conceptual framework and the vocabulary that we still wrestle with in physics classrooms today.
Well, let's unpack that vocabulary because words matter immensely when we're dealing with physics this precise.
They do.
I was looking through the historical documents in our stack, and Newton actually coined the term centripetal, right? Where does that specific word come from?
He did, yeah. Newton built the word directly from Latin.
Okay.
He took centrum, which obviously means center, and he combined it with peter, which means to seek.
To seek.
So literally translated, it means center seeking.
Center seeking? I absolutely love that translation because it instantly corrects a fundamental, everyday misconception people have.
Oh, completely.
When most people hear the phrase centripetal force, they imagine a force that is actively moving an object towards the center, like pulling a block towards you on a table.
Right.
But that's not what's happening at all, is it?
No, it's not even a little bit. If an object is moving in a circle, it's instantaneous velocity-like. The direction it actually wants to go at any given microsecond is always perfectly tangent to the circular path.
Like it wants to break free.
Exactly. The object's inertia is desperately trying to make it fly off in a straight line.
Wow.
The centripetal force doesn't pull it all the way to the center. It continuously yanks it off that straight path. It just pulls it inward exactly enough to bend the straight line into a curve.
Which brings us to the concept of uniform circular motion, or what physicists call UCM.
Yes, UCM.
This is where classical mechanics starts to feel like a trick question on a high school physics exam.
Oh, it really does trip people up.
Right. So imagine you have an object, maybe a ball on a string, and it's moving in a perfect circle at a perfectly constant speed. Let's say it's going exactly 10 meters per second, and that never, ever fluctuates.
Okay, got the picture.
Because the speed is constant, the layman instinct is to look at it and say, well, there is no acceleration.
Which is a completely understandable instinct.
Yeah.
But it is fundamentally false.
Yeah.
The confusion comes from how we use the word acceleration in everyday life.
Yeah.
We usually just mean speeding up.
Pushing the gas pedal.
Right. But in physics, velocity is a vector quantity. It inherently possesses two components: magnitude, which is the speed, and direction.
So in uniform circular motion, the magnitude, that 10 meters per second, does exactly the same.
Correct. But the direction is changing at every single infinitely small fraction of a second.
It's never pointing the same way twice.
It never points in the exact same direction twice. And because that velocity vector is in a constant state of change, the object is, by the strictest definition of calculus and physics, accelerating.
And according to Newton's second law of motion, if there is an acceleration, there must be a net resultant force actively causing that change.
Exactly.
Like, you can't have acceleration without a force pushing or pulling. And furthermore, that force must be acting in the exact same direction as the acceleration.
Precisely. Which in this case is inward, pointing dead center toward the origin of the circle.
Okay, so that's the concept.
But to truly appreciate the elegance of this, we need to verbally walk through the geometry of how we actually derive the formula for this center-seeking acceleration.
Yes, let's do the math.
I want to use the method outlined in the Edexcel physics textbook notes we have in the stack. It uses similar triangles, and it's just a beautiful piece of logic.
Okay, I'll play the role of the chalkboard here. Let's build this mental image. I want everyone listening to picture a simple, perfect circle.
Good. Now place a particle right on the edge of that circle.
Got it.
Now draw a line from the absolute center of the circle out to that particle. That is your radius line. Let's call it toroidal.
Okay.
Now, allow that particle to move a very short distance along the curved edge of the circle. Stop it there and draw a second radius line from the center to this new position.
Got it. So what we've drawn is essentially a slice of pie.
Yes.
We have two straight radius lines, $3 coming from the center, and the curved edge of the crust, which is the arc length the particle traveled. Let's call that curved distance delta cetus for the change in spatial distance.
Perfect.
And the angle right at the point of the pie slice, the angle between the two radii, we'll call that delta theta.
That is a perfect visualization. Now let's add the movement vectors.
Okay.
Go back to the first position of the particle. Draw an arrow pointing straight out from the particle, perfectly tangent to the circle.
So, grazing the edge.
Right. That arrow represents the instantaneous velocity vector at that exact moment. Let's call it $1.
So it's pointing exactly 90 degrees away from the radius line.
Exact. Perfectly perpendicular. Now go to the second position and draw another tangent arrow for the new velocity, v d tan e2. Now remember, we are in uniform circular motion. The speed is constant. So the physical length of those two arrows must be exactly the same. We'll just call the length $5.
But because the particle is moved around the curve, the two arrows are pointing in slightly different directions.
Right. They are slightly skewed relative to each other.
Right. Okay.
Now here is where the geometric magic happens. In your mind, take those two velocity arrows, $v1 and $2, lift them off the circle, and slide them together so their tail ends meet at a single point.
Oh, okay. So they are forming like a narrow V shape.
Yes. You've just formed a second triangle. The two long sides of this new triangle are your velocity vectors, $5.
Okay, I'm visualizing this.
Now draw a short line connecting the tips of the two arrows. That short line represents the difference between the two velocities. It is the change in velocity, which we call delta Wiesler.
And because both of those velocity vectors were originally drawn exactly 90 degrees, perfectly perpendicular to their respective radius lines, if the radius line swept through an angle of delta theta on the pie slice, the velocity vectors must have swept through that exact same angle.
You see it. The angle between the two velocity arrows is exactly delta theta.
Wow.
So look at what we have created. We have two triangles.
The spatial pi-slice triangle, which has two long sides of length arrow and an angle of delta theta.
Right.
And we have the velocity triangle, which has two long sides of length arrow and the exact same angle, delta theta.
Which means, geometrically speaking, they are similar triangles. They are strictly proportional to each other.
Exactly. And because they're similar, the ratios of their sides must be mathematically identical.
Yes.
So let's look at the pi-slice. For small angles, the ratio of the base to the side is the arc length divided by the radius. So delta SD divided by 2r.
And if we look at the velocity triangle, the ratio of its base to its side is the change in velocity divided by the initial velocity, delta V divided by $.
So we can set those two ratios perfectly equal to each other. We get delta V over $$ equals delta settle over $.
That is the mathematical bridge right there. It connects spatial movement and changing velocity.
Okay, I'm following the algebra here. Let's rearrange that to focus on what we actually want to find, which is the change in velocity delta v.
Right.
If we multiply both sides of the equation by valor, we get delta v by itself. So delta v equals delta times valor, all divided by $2.
Excellent. But remember our original goal. We aren't just looking for the change in velocity. We're looking for acceleration.
Right.
And how do we define acceleration in classical kinematics?
Well, it's the change in velocity over a specific period of time. So we need to bring a time variable, delta t, into this equation to make it about acceleration.
So we simply divide both sides of our current equation by delta t. On the left side, we get delta v divided by delta t $, which, as you just said, is the literal definition of acceleration. We'll call that a ln.
Okay, a ln. And on the right side, we get a slightly messy fraction. We get delta times $, divided by times delta t.
Let's clean it up.
But wait, if we group the delta s and the delta tac together, we get delta t divided by delta tac. That is a change in distance over a change in time, which is just velocity.
Yes.
That's just vi again.
You've got it. So substitute that second $, back into the equation. The right side becomes 5 times $, divided by $3.
Which simplifies down to the classic foundational equation for centripetal acceleration that every physics student eventually memorizes. Exclusive of v, all those v2 are $.
It's remarkably elegant when you talk through the shapes like that.
It really is. You start with pi slices and end up with a universal law.
Beautiful, isn't it?
But, you know, I was noticing in the U.S. Naval Academy derivation notes, they don't just stop at linear velocity, the $.
No, they don't.
They place a massive emphasis on angular velocity. Why is that?
Well, it comes down to practical engineering and measurement. Frankly, trying to measure the linear speed, the meters per second of a single point on a solid object that is spinning in a circle can be incredibly tedious.
Why is that?
Well, if you have a spinning wheel, a point near the axle is moving at a completely different linear speed than a point way out on the outer rim. The outer rim has to cover way more distance in the same amount of time.
Oh, right, because the circumference is bigger.
Exactly. But the entire wheel completes one full rotation in the exact same amount of time.
So it is much more consistent to measure how much of an angle the whole object sweeps through per second.
Exactly. That is angular velocity. It's represented by the Greek letter omega. Omega.
Okay, omega.
It is defined as the change in angle over time, delta theta over delta t, and it's typically measured in radians per second. The relationship between your linear speed on the rim and the angular velocity of the wheel is extremely simple. Phi moles from nega.
So the linear speed is just the radius multiplied by the angular speed.
Precisely.
Okay, so let's plug that back into our beautiful acceleration formula. If we take a v2 $, and we replace the $, with a liter omega, we get rho omega squared all over trawlers.
A lot of the squares.
Right, so the toy squared on top cancels with the single dollars on the bottom, and we are left with A equals IR omega 2.
Yes. And as the Physics Tutor online source points out, you can also express it as I os v dot omega.
Oh, interesting.
Yeah, these aren't different types of acceleration. They're all describing the exact same physical center-seeking reality. They just allow engineers and physicists to use whichever parameters like linear speed, angular speed, or radius are most easily measurable for their specific system.
Now, I have to admit, I want to push back on one conceptual thing here. Or, well, rather, I want to clarify something that always bugged me when I was learning this.
Hit me.
In our pi slice analogy, we used delta Sailor, the curved arc length, as the base of our spatial triangle.
I did.
But a triangle, by mathematical definition, has straight sides. An arc is a curve. You can't just pretend a curve is a straight line to make your fractions work. That feels like cheating.
You have put your finger on the exact reason why the derivation we just did is actually an approximation.
Ah, I knew it.
It is a very good approximation, But to make it perfectly true, we have to use calculus. The Wikipedia source provides the rigorous limit definition for kinematics.
Okay, break that down.
It states that the instantaneous centripetal acceleration vector is the limit as the change in time, delta tt approaches 0, of delta v over delta t tau.
Let's translate that limit concept into a real-world auditory analogy, because equations lose their meaning if we can't picture them.
Fair enough.
Imagine you were driving a car on a massive, sweeping, circular racetrack.
Okay, you're behind the wheel.
Right.
Let's say we look at your movement over a relatively long period, say 5 seconds.
Okay.
In those 5 seconds, your car travels a very noticeable sweeping arc along the track. If a drone was looking down at you and drew a perfectly straight line from where you started to where you ended up 5 seconds later, that straight line, the second line, is going to be noticeably shorter than the actual curved path of asphalt you drove over.
Right, and your velocity vector, like the direction your headlights are pointing, has changed quite a bit over those 5 seconds.
Yes. But now, let's apply the calculus concept of a limit. Let's shrink the window of time we are observing. What happens to your path if we only look at 1 second of driving?
Well, the curve you travel is much less pronounced. It's a tiny slice of the track. So the straight second line from start to finish is much, much closer in length to the actual curved arc of the asphalt.
Exactly. Now shrink the observation window to a millisecond, a microsecond, a nanosecond.
It gets smaller and smaller.
As your change in time, delta t approaches an infinitely small number as it approaches 0. The distance you travel along the arc mathematically converges with the straight second line. They become indistinguishable.
And in that exact same frozen infinitely small moment of time, your change in velocity vector, delta v-vor, locks in. It doesn't just point generally inward toward the infield of the track. It points perfectly, mathematically, perpendicularly inward toward the exact center of the circle.
Yes. The calculus limit defines the instantaneous acceleration. It proves that at any single frozen moment in time, the acceleration vector is perfectly orthogonal to the velocity vector.
I feel like we are really going off on a tangent here with all these orthogonal vectors,
right.
but I love it because understanding that perfect 90-degree relationship is the only way to understand what comes next.
Which is?
And what comes next is a deep dive into advanced coordinate systems that honestly made my brain hurt when I was reading through the physics stack exchange source.
Ah, yes. This is where we have to leave the comfortable, perfectly asymmetrical world of uniform, circular motion behind. We are entering a much more dynamic, complex, mathematical reality.
Okay, so here's the setup. A user on the Physics Stack Exchange forum brings up a massive mathematical conundrum regarding how we map out space.
Right.
In standard Cartesian coordinates, we map things using x and y on a grid. Easy. But in polar coordinates, we locate a point using 2 different pieces of information. Its distance from a central origin point, called Darlers, and its angle relative to a baseline, called Varphi.
Okay, yes.
The forum user notes that when you calculate acceleration in polar coordinates, one of the terms that pops out of the calculus is Varphi.
Let's decode that notation for the listener so it doesn't sound like alphabet soup.
Please do.
The Greek letter phi, Varphi, with a dot over it, simply means the time derivative of the angle.
Okay.
It is exactly the same concept as the angular velocity omega that we just talked about. How fast is the angle changing?
Got it.
And the hat with a little hat over it is what we call the radial unit vector. It is simply a tiny mathematical arrow pointing from your origin point straight out to where the object is.
So if we look at that formula again, it is literally just negative dollars times omega squared pointing outward.
Yes.
Which means the negative sign flips it around to point inward, back toward the origin. Conceptually, that looks exactly like our centripetal acceleration formula. A equals to omega to a tori. It's pointing to the center. So I was reading this thinking, what is the user's problem?
The problem, as the astute user points out, goes back to our definition of the word centripetal. We just established that true centripetal acceleration must be perfectly orthogonal 90 degrees perpendicular to the object's trajectory. Right. But the question is that radial unit vector, the line pointing from your origin to the object, always perfectly orthogonal to the object's path?
Well, if the object is moving in a perfect circle and you place the origin of your map exactly dead center in the middle of that circle, then yes, the radius is always perpendicular to the edge.
But what if it isn't? What if the object is following an elliptical orbit like a planet? Or what if it's a fly buzzing in a completely random squiggly path around your room?
Oh, I see.
You can still use polar coordinates to track that fly.
Yeah.
You pick an origin, say the corner of your desk. You track its distance, its dollar, and its angle, but suddenly your radius line from the desk is not crossing the fly's flight path at a perfect 90-degree angle.
Right. If the fly is darting toward the window, the line from my desk might hit its path at, like, a 45-degree angle.
Exactly.
Which means that inward-pointing vector from the formula is no longer pointing perpendicular to the fly's velocity. It's just pointing back to an arbitrary origin point I chose on my desk. So calling that specific mathematical term the centripetal acceleration is technically wrong, unless the path happens to be a perfect circle centered on your origin.
Precisely. It is a false centripetal force born from a rigid coordinate system. And this exact dilemma is where a respondent on the forum, a physicist named Walter Moretti, introduces one of the most powerful and conceptually beautiful tools in geometry.
The osculating circle,
Yes.
also known as the kissing circle. That comes from the Latin word osculare, which means to kiss.
It's a very poetic name for a rigorous mathematical construct.
Yeah.
To truly find the actual centripetal acceleration of an object moving on an arbitrary squiggly curved path, you cannot rely on a fixed origin point on a map.
Okay.
You have to decompose the object's total acceleration using something called an intrinsic orthonormal frame.
Let's build this intrinsic frame for the listener because it's a brilliant way to view motion. Instead of laying a fixed XY grid over the whole room, you essentially attach the coordinate system to the moving object itself. The map moves with the fly.
Exactly. At any given instantaneous point on the trajectory, you define 3 unit vectors that ride along with the object. First, you have the tangent vector. This arrow points exactly straight ahead in the exact direction the object is moving at that specific millisecond.
So that's our velocity vector.
Yes. Second, you have the normal vector. This arrow points perfectly, exactly 90 degrees inward from the tangent line, regardless of where your desk or the origin of the room is.
It's totally independent of the room.
Right. It doesn't care about your map. It only cares about the curve the object is currently carving. And third, you have the binormal vector, which is perpendicular to both of those, essentially giving you your 3D depth.
So how does the kissing circle fit into this moving frame?
Think about driving on a winding S-shaped mountain road. You enter a sharp left turn. At one specific frozen point on the apex of that curve, imagine drawing a perfect circle that fits snugly against the inside of the road's curve.
Okay, I see it.
It kisses the road at that one exact point. It shares the exact same tangent line as your car, and it has the exact same rate of curvature as the road does at that specific infinitesimal point. That imaginary geometric shape is the osculating circle.
So as I drive through the S-curve, the road might tighten or widen, which means the size of that imaginary kissing circle is constantly growing and shrinking to match the road's curvature perfectly at every millisecond.
Yes. And the true center of your motion is the center of that specific osculating circle, not some fixed point on a GPS map.
Oh, wow.
The component of your car's total acceleration that points along your normal unit vector pointing directly toward the shifting center of that imaginary kissing circle, that is your true, indisputable centripetal acceleration.
That is profound. It completely changes how you understand space. The center isn't a fixed geographical place. It is a dynamic, constantly shifting mathematical ghost that exists only in relation to the instantaneous curvature of your path.
It forces you to realize that physics is fundamentally local. It cares about what is happening exactly where the object is, not how the object relates to an arbitrary grid. And this discussion gets even more wildly complex when the StackExchange user asks about rotating reference frames.
Oh boy, yes. If you are standing on a spinning turntable, like a merry-go-round, the math required to find your acceleration involves this terrifyingly complex term. It's vec omega times. It's a double cross product.
All right, let's break that down visually so the listener doesn't need to write out a matrix on a chalkboard to understand it.
I appreciate that. What is a cross product fundamentally doing?
A cross product takes 2 vectors, 2 arrows, and generates a third arrow that is perfectly perpendicular to both of them. Imagine the corner of a room where the 2 floorboards meet the wall. If vector A and vector B are the floorboards, their cross product is the vertical line of the wall sticking straight up.
Okay, that visual works. So let's look at the first part of the formula. Mech omega times mech omega is the rotation axis. So imagine a metal pole sticking straight up from the center of the spinning merry-go-round.
Right.
That vertical pole is our vec omega vector, and vector is the vector pointing from the pole out to where you are standing on the ride.
Correct. The pole and your position vector form a flat plane, like the floor of the merry-go-round. So the first cross product, vec omega times vector, must generate a vector perpendicular to both the pole and your position. What direction is that?
It would point sideways.
Yeah,
Along the edge of the merry-go-round, which is the tangential velocity vector, it points exactly in the direction you are physically traveling through the air at that moment.
Exactly. So that first chunk just gives us your velocity. Now, the formula asks us to take the cross product of the vertical pole, again, with that new sideways velocity vector.
Oh, a double cross.
Right. We need an arrow perpendicular to the straight-up pole and perpendicular to your sideways movement. Where does that have to point?
If it's flat against the floor but perpendicular to my forward movement, it has to point straight back toward the pole. It points exactly at the axis of rotation.
Yes. As the expert Walter Moretti confirms on the forum, in the specific case of a rigidly rotating frame where the axis delta omega is literally at the origin, that intimidating double cross product term actually resolves to become the true centripetal acceleration. It points perfectly to the center.
It is wild how looking at physics through different coordinate systems completely changes the visual architecture of the math, but ultimately describes the exact same physical reality.
It's all connected.
We spent all this time establishing that centripetal force is a very real, measurable, center-seeking phenomenon, which naturally brings us to the most infamous, aggressively debated concept in all of circular motion.
Ah, yes. The phantom force, the impostor of classical mechanics.
Centrifugal force. According to both the PatSnap Eureka database source and the Live Science article in our stack, there is a hard, fundamental difference between centripetal force, which is real, and centrifugal force, which is largely considered fictitious.
It is considered fictitious within the strict realm of classical inertial Newtonian mechanics, yes. Let's define exactly what it is.
Please.
Centrifugal force is an apparent outward-pointing force that seems to push an object away from the center of rotation. But it doesn't come from a fundamental interaction like gravity or electromagnetism. It arises purely from a body's own inertia when observed from within a rotating frame of reference.
Let's look at the math for a second, because this is where people get confused. The PatSnap source gives the mathematical formula for centrifugal force as phi OC able m parallel anoga 2 obey do r, wait a minute, mass, angular velocity squared, and radius. That uses the exact same variables as our centripetal force equation.
It does. It calculates to the exact same magnitude of force. The only difference is the vector direction. It is the exact same math, just pointing radially outward instead of inward. It represents a shift in perspective.
Okay, let's use the live science examples to anchor this conceptually, because shifts in perspective can get abstract. The classic, universally understood example is swinging a rock on the end of a string.
Let's look at it from two perspectives. First, the inertial frame. Imagine I am standing perfectly still a few feet away, watching you swing the rock.
Okay.
What I see is your hand pulling on the string. The string exerts physical tension, a real, measurable centripetal force, pulling the rock inward, forcing it to deviate from a straight line and travel in a circle.
The rock wants to fly away, but the string says no.
Exactly. But now, let's change our reference frame. Imagine you have an ant riding on that rock. To the ant, its environment is the rock.
Yeah.
If the ant doesn't look at the background, it doesn't feel like it is accelerating inward toward your hand.
Because it's spinning with it.
Right. What the ant feels is a massive, invisible force trying to fling it outward, trying to rip it off the surface of the rock away from the string.
That terrifying feeling of being flung outward is the centrifugal force, but what you're saying is there is no actual force field pushing the ant. There is no physical hand pushing it from the inside out.
None at all.
It is simply the ant's own mass. Its inertia desperately wanting to travel in a straight line, while the surface of the rock constantly denies it that straight line by curving underneath it. It is entirely a figment of your inertia.
It absolutely is. And a more visceral example for humans is the Gravitron amusement park ride.
Oh, I remember those.
You walk inside a large cylinder, put your back against the padded wall, and the whole room starts to spin rapidly. Within seconds, you are pinned against the wall so hard you can barely lift your arms. You feel this intense, crushing pressure pushing you outward.
Right. It feels like artificial gravity pushing you into the padding.
But the physicist, standing outside the ride, sees something completely different. They see your body trying to fly off in a straight line tangent to the circle. The real force in that scenario is the rigid wall of the ride, physically pushing inward against your back.
Wow.
That normal force from the padded wall is the centripetal force constantly shoving your body toward the center to keep you moving in a circle. Your brain interprets it as being pushed out, but but in reality, the wall is aggressively shoving you in.
Okay, so from a purist physics standpoint, it's an illusion of inertia. But I have a major pushback here, and this goes to the heart of applied science.
Go for it.
If centrifugal force is entirely fake and just an illusion, why do engineers rely on it to design real physical machines? The PatSnap Eureka document specifically lists industrial centrifugal governors and passive braking devices. If the force isn't real, how can it physically push heavy metal brake rollers against a friction drum to generate actual braking torque? You can't stop a machine with an illusion.
That is the perfect pushback, and it highlights a crucial divide between theoretical physics and engineering reality. It all comes back to reference frames.
Okay, explain that.
In a non-inertial reference frame meaning, if you are an engineer designing the internal components of a machine from the perspective of the spinning rotor itself, the centrifugal force operates, mathematically and physically, exactly like a real force.
It's because the parts in the machine don't know they are spinning relative to the Earth. They only know the forces acting within their local environment.
Yes. To the metal brake rollers sitting inside the spinning drum, the outward push they experience is functionally indistinguishable from the pull of gravity.
That makes sense.
Engineers absolutely must use the centrifugal formula, fix CI equals mu omega 2R day, because in the rotating frame of that machine, that outward vector dictates exactly how stiff the retaining springs need to be and how much tensile strength the containment walls require to not explode outward. It doesn't matter one bit that an observing physicist knows, it's just inertia. To the spinning brake pad, that outward force is what dictates whether the machine functions safely or shears apart.
It's like taking a turn for the better in a car. When you round a sharp curve on the highway, the true centripetal force is the friction of your tires gripping the asphalt, pulling the massive chassis of the car inward. But you, the passenger sitting inside, are thrown outward violently against the passenger door.
Right.
The automotive engineers have to design the latch on that door to withstand a 200-pound person slamming into it with centrifugal force, regardless of whether a textbook calls your movement a fictitious force.
Exactly. The kinetic energy threatening to snap the door latch is very, very real. The label we give the force is secondary to the engineering requirement to contain it.
Okay, we've thoroughly covered the mechanics here on Earth, from amusement parks to car doors. Now I want to zoom out, way, way out.
Let's do it.
We are moving to the cosmic scale. I was reading through the Phil Sci archive paper on Newton's methodology and pairing it with the Earth and planetary physics notes. It is incredible how these equations scale up.
This is the arena where Isaac Newton's genius truly locked the architecture of the universe together. It's important to understand the historical context here. Before Newton published his Principia, the astronomer Johannes Kepler had spent years meticulously observing and documenting the motions of the planets across the night sky.
Just writing down data points.
Pure data. And based purely on that observational data, Kepler established 3 laws of planetary motion. One of the most famous and perplexing was Kepler's area law.
Right. The area law states that if you draw an imaginary line from the center of the sun to the center of a planet, that line will sweep out equal areas of space in equal amounts of time.
Okay, map that out for us.
So, when a planet is very far away from the sun, it moves quite slowly along its orbit. The pie slice it sweeps out over a month is very long but very narrow. Conversely, when the planet's orbit brings it close to the sun, it whips around much faster. The pie slice for that month is very short, but incredibly wide.
Right.
Kepler's math proved that the total square mileage of those two completely different pie slices is absolutely identical.
Kepler knew that it happened because the observational math proved it, but he had no idea why it happened. What was the physical mechanism causing the planets to change speeds?
Enter Isaac Newton.
Exactly. In his Principia, specifically propositions 1 and 2, Newton proved mathematically that Kepler's area law is valid if and only if there's a continuous centripetal force directed toward a fixed center.
So Newton used the geometric reality of these sweeping areas to prove the existence of an invisible tether pulling the planets toward the sun. He proved gravity via geometry.
Yes. He deduced that a centripetal force was both a necessary and a sufficient cause for the area law to exist. He then took his brand new law of universal gravitation and he equated it directly across the equal sign to the centripetal force equation that Huygens had developed years earlier.
Let's look at that equation from the planetary physics source because it's the bedrock of orbital mechanics.
Let's hear it.
On one side, we have the gravitational pull, big dollars, which is the universal gravitational constant times little dollars, the mass of the satellite, times big ballers, the mass of the Earth, all divided by $2, the distance between their centers squared.
Yeah.
And Newton set that exact gravitational force equal to the required centripetal force to keep it in a circle. 1 atomone of V2 narlars.
Notice a critical detail in that equation. The little dollars, the mass of the orbiting satellite, appears on both sides of the equal sign.
Oh, which means it mathematically cancels itself out entirely.
Yeah, it does.
The mass of the satellite is irrelevant to its orbit, which means the velocity required to maintain a stable orbit depends entirely on the mass of the planet it's orbiting and how far away it is. A wrench dropped by an astronaut and a 400-ton space station require the exact same velocity to maintain an orbit at the exact same altitude.
Precisely. The inertia of the mass perfectly balances the gravitational pull on that same mass. And we must be extremely careful with that distance variable, $2. As the source notes, per dollar is not simply the altitude of the satellite above the ground.
Oh, because it's from the center.
Right. The math only works if the $2 is defined as $2 plus h'ers, the radius of the Earth plus the altitude. The centripetal force tether must be calculated from the absolute center of mass of the planet, not its surface.
But as we mentioned with Kepler, planetary orbits aren't usually perfect circles. They are ellipses, ovals.
Which is where the distance $3 becomes a dynamic, shifting variable. In an elliptical orbit, the planet or satellite gets closer and further away. We define the closest point to Earth as the perigee. The mathematical formula for perigee distance is $3 is equal A1 epsilon, where A is the semi-major axis, the longest radius of the oval, and epsilon is the eccentricity of the orbit.
Eccentricity is basically just a measure of how squished or stretched out the oval is compared to a perfect circle, right?
Exactly. And eccentricity 0 is a perfect circle. As it approaches 1, it becomes highly stretched. Now, the furthest point in the orbit, the apogee, is defined as $3 A1 plus epsilon. Because $3 is physically changing as the satellite travels, the gravitational force, which, remember, relies on $2 in the denominator, is also drastically changing. When $3 is small at perigee, the denominator shrinks, which means the gravity pulls much, much harder.
Okay, let's tie this back to the centripetal requirement. To maintain the orbit and not get sucked down into the atmosphere to burn up, the required centripetal force must perfectly match that increasing gravitational pull. And since our formula is y dollar is 4 itself into v2 r3 if the force goes up, the velocity dollar must increase drastically when $3 gets small.
This is the dynamic, physical reality behind Kepler's time of flight equation. The satellite must travel vastly faster when it's closer to the Earth because the angular velocity is continuously automatically adapting to the changing radial distance and the shifting strength of the gravitational vector. It is a self-balancing cosmic dance.
That is mind-bending in its precision. But if you want something truly reality-breaking, we have to talk about the massive tangent included at the bottom of the Wikipedia source document.
Yes.
Relativistic centripetal force.
You can't do a thorough deep dive into advanced physics without eventually bumping into Albert Einstein and relativity.
So, up to this point, we've been using classical physics. FDA, MDAA, Dide, Oda, Omega. But what happens if an object, say a subatomic particle in a massive super collider like CERN, is moving in a circle at a significant fraction of the speed of light? Newton's rules start to fray at the edges, don't they?
They don't just fray, they fundamentally break down.
Yeah.
Because as you approach the speed of light, the universe stops playing by linear rules. You have to account for relativistic momentum. The equation for centripetal force has to be rewritten to include a new variable. It becomes it becomes fevia
The Greek letter gamma, the Lorentz factor.
Yes. Gamma is the mathematical key to special relativity. It is defined as $1 divided by the square root of 1v2t $2.
Let me talk through the implications of that fraction, because this is where physics feels like magic.
Please do.
In that denominator, we have v2c day $2. The object's velocity squared over the speed of light squared. As the particle's velocity gets closer and closer to CELR, that fraction approaches $1, which means the denominator of the Lorentz factor becomes the square root of $1, which approaches 0. And mathematically, $1 divided by a number approaching 0 skyrockets toward infinity.
Correct. So what does that mean for our super collider? It means the required centripetal force to keep that speeding particle moving in a circular path is no longer just 1r dotty for your dollar. It is that classical value multiplied by an exponentially growing Kamana factor. The force is now defined as the rate of change of relativistic momentum, which scales with gamma.
Let me throw a philosophical speculative idea at you based on this.
Go ahead.
We know that time dilation is inherently built into the Lorentz factor. A clock attached to that fast-moving particle in the collider is literally ticking much slower relative to the scientists standing in the lab looking at it. Does that warping of time itself literally alter the physical force required to bend its path?
In a very profound way, yes. Think about the definition of acceleration. It is a change in velocity over a change in time. If the fundamental passage of time itself is warping and stretching between the reference frame of the particle and the reference frame of the lab, the application of force necessary to change the momentum vector in that warped spacetime becomes infinitely harder.
Wow.
To the particle, in its own slow-ticking frame, it might feel like it's taking a standard, manageable turn. But from the lab's perspective, observing in real time, it requires an astronomically huge amount of magnetic force to bend the trajectory of a particle whose relativistic momentum is aggressively approaching infinity. You are fighting the curvature of space-time itself just to keep it in a circle.
That is just staggering. We went from dropping wrenches from satellites to bending space-time near the speed of light. Now, I want to rip the steering wheel in the complete opposite direction.
Okay.
We looked at the massive and the impossibly fast. Let's look at the impossibly small, down to the fundamental building blocks of the universe. We are pulling from the BPA notes on the Bohr model of the atom.
This is perhaps one of the most beautiful syntheses in all of physics. We are going to see how the exact same center-seeking geometric logic that holds Jupiter in a stable orbit dictates the physical existence of matter itself.
Setting the stage. In 1913, physics was in a state of crisis. Niels Bohr presented a brand new model of the hydrogen atom based on a few fundamental postulates. His first major postulate stated that electrons move around the central nucleus in circular, non-radiating orbits, which he called stationary states.
Now, why was that a crisis? Because classically, if an electron, which is a negatively charged particle, moves in a circle, we know it is constantly changing direction, which means it's accelerating. And according to Maxwell's widely accepted equations of electromagnetism, an accelerating charged particle must emit electromagnetic radiation. It must bleed off energy in the form of light.
And if it's constantly bleeding off kinetic energy, it should slow down, lose its orbital velocity, and instantly spiral crash into the positive nucleus.
Exactly.
The atom should collapse in a fraction of a millisecond.
If classical physics ruled the atom, solid matter could not exist. Atoms would self-destruct instantly, which means Bohr had to introduce radical new quantum rules to override classical electromagnetism and explain why the electron doesn't radiate energy in these specific orbits.
Right.
But, and here's the genius part, to find the physical size of these allowed orbits, he didn't throw out classical physics entirely. He still relied absolutely on classical centripetal force.
He used the old tools to build a new universe. For an orbiting electron with mass dollars and velocity dollars, there has to be a physical inward force keeping it tethered in a circle, just like gravity tethers a satellite.
Yep.
But in the atom, the tether isn't gravity, it is the electric force. The electrostatic attraction between the positive nucleus and the negative electron. The Coulomb force.
I know you have a text in front of you. What is the formulation for that Coulomb source?
Okay, the source outlines the Coulomb force equation as Z dot E22 divided by $4 pi epsilon R22. Let's break that down without getting bogged down in the alphabet.
Good idea.
Basically, ZODAL is the number of protons, which is 1 for hydrogen. Azol is the electric charge. Epsilon is a constant describing the vacuum of space, the permittivity, and $3 is the radius, the distance between them. Bohr took that entire calculation for electrical magnetic pull, and he set it exactly equal to our old friend, the centripetal force requirement, dot V2R RA2 per pi epsilon R2 per. Look at the structure of that. It looks conceptually identical to the satellite equation we discussed earlier, just swapping out masses and gravity for electrical charges and permittivity. The classical balance holds, but Bohr's true stroke of genius was the very next step. His postulate said that the angular momentum of the electron, $, is quantized.
Quantized meaning discrete steps.
Right. It isn't a smooth sliding scale. It can only exist in rigid integer multiples of a basic fundamental unit. Planck's constant divided by 2 Pibler, so $y is an integer like 1, 2, 3, representing the orbit levels.
And from classical mechanics, we already know angular momentum is defined as b8 a t go b a do, mass times velocity times radius. Yeah. So he set them equal. T do d a t do n d t a t do h.
The source notes a really beautiful underlying condition here later developed by de Broglie regarding waves. These integer steps aren't arbitrary. Only orbits that can fit an exact integral number of electron wavelengths around the perimeter are allowed to exist. Window ATO is a standing wave. It is a profoundly visual concept. The electron isn't just a tiny solid marble orbiting like a moon. It acts as a wave of probability, and that wave must perfectly connect with itself as it wraps around the circular circumference of the orbit.
Like it has to line up.
Exactly. If the orbit size is wrong, the wave doesn't meet perfectly end to end. The peaks hit the troughs, it destructively interferes with itself, and that orbit physically cannot exist. It's like a snake perfectly eating its own tail.
Okay, I want to walk through the algebraic substitution from the source conceptually because it leads to one of the most important fundamental constants in all of physics.
Let's do it. We have our two equations, the force balance and the quantum angular momentum. We need to get rid of the velocity variable, $5, to solve for the radius. From the momentum equation, if we isolate $5, we get $5 equal NMIH, 2 ball F2 dollar.
Now, take that entire chunky expression for $5 and substitute it into the V Toddy 2 spot in the centripetal force equation.
I won't read all the squares and pi symbols aloud because it gets messy, but basically you square all the quantum terms, multiply by the mass over radius, and set it against the electrical Coulomb force.
Right. When you churn through that algebra, simplifying the fractions and rearranging everything to isolate $2, all the chaos falls away and something beautiful emerges. You get 20 epsilon h 2 delta n t dot e2 and cf dot n2.
And if we look at the very innermost, smallest possible orbit, the ground state, where $1 equals $1 and $2 just becomes a baller and vanishes, what we are left with is a collection of pure constants. $t equals epsilon dollar dot e2, that is the Bohr radius.
The fundamental baseline size of the hydrogen atom, derived by perfectly balancing the classical inward electric pull against the classical outward requirement of centripetal inertia, but strictly gated by the quantum requirement of geometric standing waves.
It's actually incredible that the exact same algebraic math used to launch a weather satellite into orbit is what Bohr used to figure out the physical size of an atom.
It's universal.
It proves the size of an atom isn't just random, it's a strict mathematical equilibrium. It makes the universe feel much more cohesive. The physics of the massive planets and the minuscule atoms are inextricably tethered together by the geometry of the circle.
It is the ultimate unification of concepts, which I think pivots us perfectly into the practical application of all this theory. Because physicists don't just calculate these centripetal forces on chalkboards, we harness them aggressively in the real world. Let's look at some practical physics.
I want to start with the most wonderfully low-tech, nostalgic experiment from our stack. I was reading through the OCR A-level physics notes, and they detail an experiment called the whirling bung.
Ah, yes. It is a staple of high school physics classrooms worldwide for a very good reason.
It's so simple. You take a rubber bung like a stopper for a test tube, and you tie it securely to a piece of string. You thread the other end of the string down through a hollow glass tube. Then you hang some heavy metal washers or weights on the bottom end of the string. The student holds the glass tube vertically and swings the rubber bung around in a horizontal circle above their head.
The goal here isn't just to play around. It is rigorous empirical testing. We have this theoretical equation we've been discussing. $1 equals no swek win d 2r dollars. The whirling bung experiment lets a student physically verify that the squared relationship actually exists in the real world.
Let's trace the forces. The tension in the string is providing the centripetal force, $5, pulling the bung inward, and that tension is exactly equal to the gravitational weight of the metal masses hanging statically at the bottom, which is mass times gravity, not dollars. So as long as you don't change the weights, your force $5 is a known constant. You keep the radius dollars constant by placing a little marker tape on the string and ensuring the tape doesn't move up or down relative to the glass tube while you spin it.
Right, so if $5, the mass of the bung dollars and the radius dollars are all constant, then according to the math, your velocity dollars must be forced into a constant equilibrium. But the experiment asks, what happens if the student tries to forcefully skin the bung faster?
If velocity increases, the V$2 term in the equation goes up exponentially. The required centripetal force to keep it in that tight circle skyrockets. But wait, your hanging weights at the bottom haven't magically gotten heavier. The available tension is suddenly no longer strong enough to provide the desperately needed centripetal force.
The system fails. The motion is no longer dynamically stable.
The inertia of the bung wins the tug of war. The bung will fly outward, pulling the string violently up through the glass tube, lifting the heavy weights, and physically increasing the radius twice until a new mathematical equilibrium is reached with the higher velocity. If a student isn't paying attention, it will literally bung up the works of their carefully measured experiment.
Huh. That is an immediate tactile demonstration of why the 2-polar-2 term is so dominant, but it's fascinating to realize that this exact same basic string and weight principle scales up to engineer some of the most advanced, high-stakes biomedical equipment in the world. I was looking through the AELAV specifications you shared.
Right. A modern laboratory centrifuge is essentially the ultimate spin doctor. It utilizes intense rotational speed to separate microscopic substances based purely on tiny differences in their density. The AELAV source manual is very careful to outline the critical difference between RPM and RCF. Why is that distinction so important for a lab tech to know?
Because one is a setting, and the other is the actual physics happening to the sample. RPM is just revolutions per minute. It is simply a measure of angular speed. But RCF stands for relative centrifugal force. It is the actual measurement of the g-force, measured in multiples of standard Earth gravity, xg.
RCF is what actually matters to the biology in the test tube because it accounts for the radius of the machine's rotor. As our Formula $1 omega-2RR explicitly shows, if two different centrifuges in a lab are set to spin at the exact same RPM, but one machine has a rotor twice as wide as the other, the samples in the wider machine are experiencing twice the centrifugal force. The radius changes the physical reality of the spin.
Exactly. In these machines, we are aggressively taking advantage of that fictitious centrifugal force we debated earlier. From the frame of reference of the biological sample sitting inside the spinning test tube, it feels an immense crushing gravitational pull directed toward the bottom of the tube. Denser, heavier cellular materials are forced outward, which translates to downward toward the bottom of the tube faster and with much more force than the less dense fluids. It artificially amplifies buoyancy.
AELAB details several specific machines designed for very different tasks based on these physics. They have a low-speed centrifuge, the AELSC, which operates between 300 and 4,000 RPM. This is designed for standard clinical labs separating blood serum, plasma, and urine.
Right.
It uses a brushless DC motor, so it's a quiet, reliable workhorse.
Right, because blood cells are relatively large and heavy compared to the plasma they float in. They don't require an extreme amount of artificial gravity to settle out. But if you move to molecular biology and you need to physically isolate DNA from a cellular solution, 4,000 RPM is going to do anything. DNA molecules are incredibly light and highly miscible. They want to stay in solution.
To rip them out, you need the high-speed mini-centrifuge, the AEMC-15. This machine hits 15,000 RPM, which generates a staggering RCF of 15,100 xg.
Over 15,000 times the force of Earth's natural gravity. That is the sheer magnitude of kinetic force it takes to physically yank a microscopic DNA molecule out of suspension and force it to pellet at the bottom of a tube. You're using brute force mechanics to overcome molecular bonds.
And then there are highly specialized niche designs like the mini-plate centrifuge MPC-22. It spins at a modest 2,200 RPM, generating 480 xg, but its rotor is specifically rectangular to accommodate flat PCR plates instead of tubes.
Oh, that's clever.
Its sole critical job is to quickly spin down tiny errant droplets of liquid and condensation clinging to the upper walls of the microscopic wells, forcing them down into the main mixture at the bottom before you put the plate into a thermal cycler for a DNA reaction.
If those droplets stay on the walls, the reagent concentrations in the bottom are wrong and the experiment fails. It is precision biological engineering based entirely on controlling V severe dollars to manage fluid dynamics at a microscale.
And if you think controlling microscopic drops of fluid is impressive, wait until you see this at an industrial scale. We are moving from isolating micrograms of DNA to processing thousands of liters of raw material an hour. I was reading through the Neologic Engineers documentation on their milk cream separator.
The application of centrifugal force in mass manufacturing is a massive hidden cornerstone of the modern global economy.
We are quite literally skimming the surface of fluid dynamics here. Think about raw cow's milk straight from the farm. It is an emulsion, a mixture of heavier water-based skim milk and lighter fat globules, the cream. Under normal 1G in Earth gravity, if you just pour raw milk into a bucket and leave it in a cold room for 24 hours, the cream eventually gathers at the top due to those slight density differences. The heavier liquid sinks, displacing the lighter fat upwards.
But modern commercial dairies processing millions of gallons a day don't have 24 hours to wait for a bucket to settle. They need to drastically amplify that gravitational separation to keep the supply chain moving.
So they use a centrifugal separator. Neologic describes a massive stainless steel unit containing a dense stack of conical discs spinning inside a drum at anywhere from 6,000 to 10,000 RPM. They are truly milking it for all it's worth.
The fluid dynamics occurring inside that drum are fascinating to visualize. As the raw milk is continuously pumped through these rapidly spinning conical discs, it is subjected to a centrifugal force thousands of times stronger than normal gravity. The heavier skim milk is aggressively, violently pushed to the outer walls of the spinning drum.
And the fat globules, the cream, because they are lighter and have less inertia, are literally displaced inward. The heavy milk crowds them out, forcing the cream to seek the center axis of the drum.
It is a brilliant, continuous flow process. The heavy skim milk bleeds out through ports on the outer edges, while the lighter cream flows up and out through the very center. But it requires incredibly strict environmental control. The manual notes the optimal temperature must be exactly 45 degrees Celsius.
Why is that?
Well, if it's too cold, the viscosity of the fat is too high, it clumps, and the centrifugal force can't push it through the fluid matrix efficiently.
And when it's dialed in, the efficiency is almost unbelievable. A high-quality separator running at speed removes the cream so effectively that it leaves only 0.05% fat behind in the skim milk. By the way, the source notes a really fascinating tangent about goat milk versus cow milk that highlights the physics perfectly.
Oh, the microstructural differences.
Yes. Goat milk has a naturally different microstructure. The fat globules in goat milk are physically much smaller than the ones in cow milk. Because they are smaller, they have even less mass, which means gravity has a much harder time acting on them. If you leave goat milk in a bucket, it takes vastly longer to separate naturally than cow milk. Some people call it naturally homogenized. But when you pump that same goat milk into a disc bowl centrifuge,
the extreme forces involved completely override the microstructural resistance.
Right.
When you apply 10,000 Gs, it doesn't matter how small the fat globule is. The density difference is magnified to such an extreme that the goat milk separates just as rapidly and efficiently as the cow milk. The math conquers the biology.
The source also highlights the brutal engineering realities of handling the organic byproducts of this process. They mention solids retaining separator versus self-cleaning separators.
Okay.
In a solids retaining machine, all the microscopic dirt, somatic cells, and heavy organic slime are pushed to the absolute outer wall and get trapped there. The machine has to be shut down, opened, and manually scrubbed out.
That sounds tedious.
It is. But in large-scale dairy lines, they use self-cleaning centrifuges that actually open small ports on the outer edge for a fraction of a second while spinning at full speed, using the massive centrifugal force to violently shoot the accumulated slime out into a catch basin, allowing for continuous 24/7 uninterrupted operation.
It's an incredible piece of mechanical engineering, utilizing the physics to clean the machine itself.
We've talked about separating liquids, but the industrial applications of these kinematic laws just keep going to completely different mediums. I was reading through the REMBE Ultimate Weighing Solution presentation. This poses a really interesting logistical problem. How do you accurately weigh thousands of tons of bulk, solid material while it is in continuous rapid motion falling down a production line? It's a weighty matter.
You can't exactly ask a waterfall of grain to stop and sit patiently on a static bathroom scale. You have to use dynamic weighing. Specifically, REMBE uses impact technology based entirely on our core topic, centripetal force.
The REMBE presentation highlights an inline weighing device that features a specifically engineered curved metal measuring chute. As the bulk material, whether it's grain, chemical powder, whatever, slides continuously over this curved surface, the geometry of the chute literally forces the flowing material into a temporary circular path.
And because the engineers designed the chute, they know the exact mathematical radius of that curve, $3. And they have sensors to measure the velocity of the material flowing over it, $5. From our fundamental physics equations, we know absolutely that in order for that physical mass to negotiate that curve and not fly straight through the metal, it must exert a reactive centrifugal force outward against the surface of the chute. That reactive force, $5, is exactly equal to $1 V2R dollars.
So by mounting the curved chute on highly sensitive electronic load cells that constantly measure that exact outward physical force, the computer system can instantly, continuously back-calculate the algebraic equation to find dollars. It calculates the exact mass of the material flowing over it in real time.
It is an incredibly elegant, frictionless solution. They are using the object's own inertia to weigh it, and the benefits they list are massive for industrial logistics. It offers extremely high accuracy, reliable repeatability, and a very compact installation footprint compared to the massive, sprawling conveyor way belts historically used in factories.
The presentation shows these systems installed across wildly diverse industries. They have them in malting facilities, accurately weighing torrents of grain. They use them in harsh recycle streams handling rough, unpredictable particulate matter, and they even use them to get to the heart of the batter in chocolate processing. We're dealing with sticky viscosity, and ensuring continuous, unbroken flow is absolutely critical to the product.
It is brilliant engineering. By simply forcing a chaotic product into a strictly controlled geometric curve, they force the universe to reveal the product's mass through the undeniable laws of kinematics.
Which, mathematically speaking, brings us perfectly full circle on today's deep dive.
A fitting shape for the journey.
It really has been a staggering exploration. We started by stripping away the comfort of the straight line, looking at the abstract geometric calculus of uniform circular motion. We visualized pi slices and velocity vectors, watching an imaginary second line shrink down to a limit of 0 to reveal a perfectly orthogonal center-seeking acceleration.
We waded through the treacherous, shifting maps of polar coordinates and discovered that the true center of any motion isn't a fixed location, but is dictated by the dynamic, ghostly presence of the oscillating kissing circle.
We tackled the great debate of centrifugal force, recognizing it as the terrifying feeling of inertia being denied by a curve, while simultaneously acknowledging its absolute, undeniable physical reality for the engineers tasked with building non-inertial systems like brakes and containment walls.
We watched Isaac Newton utilize this exact same sweeping geometry to bind the planets to the sun, proving that an elliptical orbit requires velocity to continuously, violently adapt to match a constantly shifting gravitational tether. We even saw how the warping of time and relativistic momentum fundamentally alters the required force for particles approaching the speed of light.
We shrunk our perspective down to the quantum realm, observing the genius of Niels Bohr as he balanced raw electrostatic attraction against classical centripetal inertia, gated by the standing waves of probability, to define the exact physical radius of a hydrogen atom.
And finally, we returned to the macroscopic world to see these exact same mathematical forces harnessed to isolate microscopic DNA in a 15,000-gram lab centrifuge, separate fat from milk at 10,000 RPM, and dynamically wave-flowing chocolate on a production line using curved geometry. The sheer universal scope of phi dollars and VV part is just breathtaking.
It connects everything. But before we wrap up and let you go, I know you brought a final, incredibly complex thought experiment derived from all these sources to leave the listener chewing on.
I did. It ties several of these extreme concepts together. We talked briefly about non-inertial frames in astronaut training earlier.
Right. NASA famously uses those massive spinning room-sized centrifuges to pin astronauts to their seats, safely simulating the extreme, crushing acceleration G-loads of a rocket launch while staying on the ground.
Yes. In that training centrifuge, the math is relatively stable. The mass of the astronaut sitting in the chair is constant. The radius of the mechanical arm is constant. The engineers just crank up the angular velocity of the spin to increase the simulated G-load. But think about what is actually happening to a real rocket during a vertical launch. A rocket is unique because it is continuously, violently losing massive amounts of mass. It is burning thousands of pounds of chemical fuel every single second.
Okay, I'm tracking.
According to Newton's second law of $5 equals more dollar, the raw thrust of the rocket motors, the pushing force, remains relatively constant as they burn. But the total mass of the vehicle is dropping drastically every second. Therefore, to keep the equation balanced, the acceleration, a rocket must physically skyrocket as the rocket ascends.
Right. The life science source specifically noted that the physical acceleration toward the end of a rocket's boost phase increases to several times normal gravity, simply because the rocket chassis is now nearly empty and incredibly light, but the engines are still pushing with maximum world-ending thrust.
Now, here is the thought experiment.
Yeah.
Take that aggressively accelerating, rapidly mass-shedding rocket and view its trajectory from the intrinsic orthonormal frame of an oscillating circle in space as the rocket begins to perform an orbital insertion burn, a maneuver where it intentionally flies in a sweeping curve to enter orbit.
Oh, wow. Okay, the variables are colliding.
Because the mass of the ship is continuously and drastically decreasing, the required centripetal force to hold that specific curve is dropping. But the linear forward acceleration is concurrently increasing wildly due to the thrust-to-weight ratio. How does this continuous violent shedding of mass dynamically redefine the real centripetal force the maneuvering thrusters must precisely provide to not overshoot the curve, while simultaneously redefining the apparent centrifugal force physically pinning the astronaut to their seat at every single given millisecond of that maneuver?
It is a calculus nightmare. It is a problem where literally every single variable in our core equation, mass, velocity, the radius of the local curvature, and the resultant acceleration, is drastically changing simultaneously.
Exactly. It requires continuous real-time integration just to know exactly how hard the astronaut is being pushed into the cushions.
That is a beautiful, deeply terrifying physics problem to mull over. It really proves the overarching lesson of today. The closer you look at a simple curve, the more infinitely complex the mechanics of the universe become. Thank you for joining us on this highly mathematical, incredibly expansive deep dive into the physics of rotation. Keep questioning the physical reality around you, keep looking for the invisible forces pulling you toward the center, and we will see you next time.